Good day, dear friends. Hope this finds you in the best of spirit. I'm Pranasish. I'm here to help you understand instantaneous velocity and instantaneous acceleration in curvilinear motion. In the past two videos, we found the expressions and the definitions of two very important unit vectors. One is unit tangent and other is unit normal. The rate of change of the position with respect to the distance is equal to the unit tangent, and the rate of change of the unit tangent with respect to the distance is equal to the reciprocal of the radius of curvature multiplied by the unit normal. To have much better understanding of the instantaneous velocity and the instantaneous acceleration of a particle in the curvilinear motion, you should, with minute attention, watch the corresponding videos in which these two expressions have been beautifully deduced with detailed explanation. And I hope you do so. The corresponding links have been given in the description box. This is a curved path followed by a particle. P is any point on the curved path. We are going to find the expressions for the instantaneous velocity and the instantaneous acceleration of the particle at point P. S dot denotes the instantaneous speed of the particle at point P, and S dot is equal to ds dt. S double dot denotes the instantaneous rate of the change of speed of the particle at point P, and S double dot is equal to ds dot dt. Now let's find the expression for the instantaneous velocity of the particle at point P. The instantaneous velocity of the particle at point P is given by vector v is equal to d vector r dt. It is the rate of change of the position of the particle with respect to time, is equal to d vector t ds multiplied by ds dt. And thus we find the expression for the instantaneous velocity, and it is given by vector v is equal to, in place of ds dt, we write s dot, and in place of d vector or ds, we write the unit tangent. And this is the expression for the instantaneous velocity of the particle at point P. The magnitude of the instantaneous velocity is equal to the instantaneous speed of the particle, and the velocity is directed along the tangent drawn to the curve at point P. Now let's find the expression for the instantaneous acceleration of the particle at point P. And the instantaneous acceleration of the particle at point P is given by vector A is equal to d v vector dt. It is the rate of change of the velocity of the particle with respect to time, is equal to d upon dt. In place of vector v, we can write s dot unit tangent. It is a product of two variables. One of the variables is a scalar quantity and the other is a vector quantity. D s dot dt unit tangent plus s dot d vector t dt is equal to d s dot dt vector t plus s dot In place of d vector t dt, we write d vector t ds multiplied by ds dt is equal to ds dot dt vector t plus s dot. In place of d vector t ds, we write the reciprocal of the radius of curvature multiplied by the unit normal, and in place of ds dt, we write s dot. Thus we get the final expression for the instantaneous acceleration of the particle, and it is given by in place of ds dot dt, we write s double dot unit tangent plus s dot squared divided by rho, s dot squared divided by rho unit normal, and this is the final expression for the instantaneous acceleration of the particle. Now let's analyze this instantaneous acceleration of the particle. We see that the instantaneous acceleration of the particle is the vector sum of two vectors. One is the tangential acceleration of the particle, and the other is the normal acceleration of the particle. Since the unit tangent and the unit normal are mutually perpendicular to each other, we can say that this is the tangential component of the instantaneous acceleration of the particle, and this is the normal component of the instantaneous acceleration of the particle, and the normal component of the instantaneous acceleration of the particle can also be said to be the centripetal acceleration, and it's directed radially inward. The tangential acceleration is directed along the tangent drawn to the curve at point P, and the centripetal acceleration is directed along the normal drawn to the curve at point P, and it's radially inward. And the resultant is the instantaneous acceleration, and it is vector A. Now let's find the magnitude of the instantaneous acceleration, and it's given by modulus of vector A is equal to the square root of the square of the magnitude of the tangential component of the acceleration, s double dot squared, plus the square of the magnitude of the normal component of the instantaneous acceleration, and we write s dot to the power 4 divided by rho squared. Now let's find the direction of the instantaneous acceleration. From the diagram, we see that the instantaneous acceleration of the particle makes an angle theta with the normal, and the tangent of the angle theta is equal to the magnitude of the tangential component of the acceleration divided by the magnitude of the normal component of the acceleration. Thus theta is equal to the arctangent of the ratio of the magnitude of the tangential component of the acceleration, s double dot, divided by the magnitude of the normal component of the instantaneous acceleration, and it's s double dot squared divided by rho. And finally we write theta is equal to arctan or the arctangent of rho s double dot divided by s dot squared. Thus we find two very valuable expressions. One is of the instantaneous velocity of the particle and the other is of the instantaneous acceleration of the particle. From this very expression we can say that in the case of rectilinear motion, rho tends to infinity and the normal component of the instantaneous acceleration gets reduced to zero vector, and in that case the instantaneous acceleration will be equal to the tangential acceleration and the tangential direction will be along the straight line followed by the particle in the rectilinear motion. And in the case of uniform circular motion, s double dot will be 0 as the rate of change of the speed of the particle will be 0, and in that case the tangential acceleration will get reduced to 0 vector and the magnitude of the centripetal acceleration will be equal to the square of the speed of the particle divided by the radius of curvature. Hope you have got the idea of the instantaneous velocity of a particle and the instantaneous acceleration of a particle in the curvilinear motion. Thank you.